1.5 continuity in calculus. This should be quite easy and quite simple, so we're gonna go over it. And yeah. So let's go over the definition of continuity. And a function is continuous if f of a is defined, which just means f of any arbitrary point. So f of 4, f of 5, f of 6. But that means the limit as x approaches a of f of x also has to be defined, and the limit as x approaches a of f of x has to be equal to f of a. So if I had to draw a graph, sorry, that was my average velocity proof. We had something like this, and this is f of a. We'll say f of a or sorry, that wouldn't be right actually. This would be the right notation. A f of a. And the limit as x approaches f of a also has to be equal to a. And the reason being is that if f of a is defined on somewhere right here, and this is f of a, this doesn't work because the limit as x approaches a of f of a is not equal to this. So although this function does have a limit which would be right here, because remember the limit is as x approaches this point, it's not equal to this, so it's discontinuous. So that's all this thing is saying. In other words, a function is continuous if it is defined at a point, and as x approaches that point, it has the same output value. So yeah, in simple terms, you can draw a function without lifting your pen on the paper. It is continuous, which is quite self-explanatory. So yeah, we'll get into a lot more stuff. So let's go over one-handed continuity. And a function is continuous from the right at a number at a. Sorry, I think at a number a if the limit as x approaches a from the right side of f of x equals f of a, and is continuous from the left at a if the limit as x approaches a minus f of x is equal to a. So let's take, and we'll do a square root function. So limit as x approaches 0 of the square root function is undefined. The reason being is that there's nothing on the left side. There's nothing from the left side. It's there's no limit as x approaches 0 from the left side because there is nothing past 0. But we know that f of 0 is going to equal 0. And we know that as x approaches 0 from the right side, it's also equal 0. So this would be a one-hand-sided continuity. Sorry, actually that's not right. This will be a one-handed continuity side. So that's pretty self-explanatory as we all know. And that's going to be 0. So that means this function is continuous from the right side at x equals 0. And 0 would be a in this case. Or a would be 0 in this case, same thing. So remember when we did theorems of limits or limit laws, we established limits simply just because we don't have to find or redefine new functions. Instead, so like for example, we know x squared is continuous, and we might know the limit of x approaches a of x squared, which is just a squared, by the way. So instead of having to make new limit laws, instead we can just use these. And that makes it just a whole lot simpler for us. Like for example, when we use the chain rule, which we'll get to later. Actually, then maybe I shouldn't talk about that. But let's say we take the sine of x squared, and we take the limit of that. We can just use like the limit of composition rule to calculate this. Or if we do limit as x approaches a of x squared sine x, which you can use squeeze theorem for. But simply put, remember that the product is just limit as x approaches a of x squared, and the limit as x approaches a of sine x, which is sine a. Simply we can just plug the a into both points, and we don't have to redefine new definitions for the limit as x approaches a here. So it's the same thing. And these are pretty self-explanatory. F plus g, if f plus g are continuous at a, f minus g, c times f, which is the constant multiple, f times g, and f divided by g. But notice that we don't go into the composition of functions, which we'll get to later, if g of a isn't equal to 0, because if it is, then it's obviously discontinuous because it's a rational function. So polynomial are continuous everywhere. Its domain is negative infinity to infinity, as we mentioned in the previous video. Any rational function is continuous, whether it is defined. That is, it's continuous on its domain. Vertigloss exists, though, which is why we have to make the specification that it's continuous on its domain, because something like x squared minus 4, and I use this, and x minus 2 means that x isn't defined at 2. So x is not defined at 2. Proof of polynomial continuity. The limit as x approaches a of x of m is equal to a of m, and since since a polynomial is just the sum of a lot of these terms, it's continuous because we can just evaluate the limits. Or since each part is continuous, it would just be a sum of continuous terms, which is still continuous because we mentioned the definition or the theorems of continuity, which is what I said. For rational functions in the form px, again, same thing as the rational function thing. I'm not even going to get to that. Even further extrapolation, so many familiar functions are continuous at every number a. So like sine x is continuous, x squared is continuous. A lot of these simple terms, square x is continuous except at x equals 0. So a lot of these terms are actually continuous, and this book uses an example of tan x equals sin x over cosine x. Using continuity laws, it continues except when cosine x equals 0, which would be at, using some quick maths, it would be pi over 2 plus n pi over 2. If f is continuous at b, and this is a little complicated, but it's quite simple. So, I mean, that might sound like a living a contradiction, but it's not. So, if f is continuous at b, which means it's defined at b, and limit as x approaches a of g of x is b, then limit, I'm reading it because I don't have it memorized. I think that should be limit as x approaches a, so let me fix that right now. F of g of x is equal to f limit x approaches a of g of x. Wait, hold on. Let me just remove that. Let me make this simpler. Oh, wow. Okay. There we go. So this one is pretty logical. Because if f of b is defined, and the limit as x approaches a, yes. Because simply put, remember that in a composition of functions, the inside function becomes the x value. So f of g of x is the same as just g of x as the input. So then if the limit as x approaches a of g of x is b, and remember that g of x becomes a completely new input. So if it would be like x of f of x equals x, and g of x equals x squared, then f of g of x would just be x squared, and vice versa. So that means if the limit as x approaches a equals b, then that would be the same thing as f of b squared. F of b, and that's defined. So this is why the rule is here. It's a little bit complicated to understand, but in simple terms, g of x is the only thing that determines the input and output, and if the output of this is b, then that's the same thing as putting b in the input of f, which is why we do that, which is basically the same as f of b, so that's logical. Intuitively, this works because if x is close to a, then g of x is close to b, right? And then f of g of x, and since the limit as x approaches a of g of x is b, that means f of g of x as g of x is getting closer to b is f of b. Very wordy, but it makes sense to me, so I'm not going to say anything more. I think I explained that pretty well. Now, this is a new theorem, Theorem 8 actually, in my book. But these numbers are relative to my book, so I guess it doesn't matter for anybody watching this video. But if you're following along, if g is continuous at a, and f is continuous at g of a, then the composite function f of g of x equals f, I think it should be limit as x approaches a, of g of x g of x is equal or is continuous to f of g of x, because that means g of x is getting closer to a. Pretty self-explanatory. Intermediate value theorem is just so easy. Like, what is this, like, illogical? I mean, not illogical, but what is this proof? I mean, I guess they do have to establish the proofs for even the smallest things, but it's pretty self-explanatory here. So let's take a function here. So suppose that f is continuous on the closed interval a, b, and remember that an interval would be on the x-axis. So let's say this is a and b. And let n be any number between f of a and f of b. So that means this would be f of a, and this would be f of b. So since these would be, since this is continuous, that means n, which they use, I believe. And there exists a number c, so c, where n equals f of c. I mean, that's pretty self-explanatory because this is continuous, meaning that any number here should exist, and that's basically what it's saying, that any number between these two inputs, if we're on a closed interval, so like any number here has to correspond to something here, kind of like the precise definition of a limit, but it's a little bit different because here this is self-explanatory. I mean, if an output exists between two outputs, then the input which of that output should exist between two inputs. So n is an output that is between f of b and f of a, and the input that gives you n is between a and b, or the inputs. So that's self-explanatory. That's all of 1.5 really. There are a few confusing things when you read through your textbook, but just remember that this is like high school math. I mean, you'll be fine. Like, seriously. Just they try to overcomplicate things like the intermediate value theorem. But I guess they do have to establish a precise definition. So that's all for Calculus 1.5. And I'm going to be learning the lesson tomorrow. So, yeah.